speaker today is Anna Maria Raclariu from KCL. He'll talk about infinite towers of 2D symmetries from the Carrollian limit of 3D symmetry.
Thank you. It's a pleasure to be here. So I'm going to be talking about some recent work that I've done with Leonardo Di Gioia. So it's a paper from last month, but also some previous work. And it also will rely on some works with Laurent Friedel and Daniele Pranzetti. So this talk is mostly about gravity, but we are at a CFT workshop, or a really QFT workshop, so I try to explain the connections to conformal field theories more generally, and in the process I'm also going to be reviewing some work that is not mine. So for example, part 2 is going to be about some work by Shu Hengshao and Clay Cordova from a couple of years ago. Okay, so let me start by kind of trying to sketch what this talk is about. And roughly speaking, it's about some mysterious relation between gravity and conformal field theory. So at long distances, one seems to encounter some CFT properties. And of course, we are familiar with maybe such a relationship in the context of the ADS-CFT correspondence. But what I'm going to be talking about today is seems to go beyond this ADS-CFT paradigm. So let me describe it in the context in which maybe it most strikingly appears, which is the context of four-dimensional asymptotically flat spacetimes. So these are just, you should think about these as describing theories of gravity that at very long distances, where at very long distances, space-time basically reverts to Minkowski space. So this would be the setting in which you would study, for example, just the general relativity with vanishing cosmological constants, gravitational waves, and so on. So it's just Einstein gravity. Here GR is general relativity. So gravitational waves. Scattering amplitudes and so on and so forth. So to set up the problem, we can look at, so first of all, we can think about an asymptotically flat spacetime as this diamond here, which is obtained by conformally compactifying it, and the boundary is the conformal boundary, which is a null surface. It's the same as one would find if you conformally compactify Minkowski space. And in this context, it's very natural to think about the scattering of particles. So the boundaries here are usually called scribe plus and scribe minus, so future null infinity and past null infinity, respectively. So you can imagine, so the processes in which one sees, one encounters these infinite dimensional symmetries that I'm going to be talking about are the scattering in the scattering of say massless particles, including gravitons. So I'm going to make that more precise in a moment. And in this process, you can have both gravitational radiation and potentially other massless particles, and maybe also massive particles being emitted. So I'm going to be particularly interested in gravitational radiation. So how do we describe this? Sorry, and I should say, so in 4 dimensions here, very naturally, it's very natural to work with a very convenient set of coordinates, which are called boundary coordinates. So in particular, there is a retarded time u, which is t minus r, where t is the usual Minkowski time, and r is the radial coordinate in Minkowski time. There is some advanced time here at past null infinity, and then there are some transverse coordinates on these spheres. So these are 2 spheres. I'm I'm going to label these coordinates on the 2 sphere by omega. So how do you describe gravitational radiation? So this can be extracted by performing, so I should say here that usually interactions are assumed to be localized in space and time. So as one moves farther and farther away from the place at which the interactions happen, one should expect to be in a region which is approximately Minkowski space, plus linear and quadratic and so on perturbations around this Minkowski background. So this is exactly the context in which we study gravitational waves. We think about them as just linearized metric perturbations on top of the Minkowski background. And in particular, they are transverse traceless components of these of the metric. So there are 2 degrees of freedom. There's positive and negative helicity gravitons. It follows from the usual analysis of representations, massless representations of the Poincaré group. So we usually introduce polarization tensors in space-time that one can use to project onto these radiative degrees of freedom. So plus and minus will denote the 2 helicities. And h mu nu is going to be this metric perturbation. So the full metric g mu nu is going to be assumed to be eta mu nu plus gravitational coupling times h mu nu plus other terms leading in this coupling. So hopefully this is all standard, and now the idea is that to one can construct a scattering amplitude in the usual way, as one would construct a scattering amplitude of, say, of fields in Minkowski space by basically computing a Fourier transform, or really mode expanding this object, which behaves very much like a free field at long distances. So if we take e to the IPX, we're going to pick up creation and annihilation operators from this object, which we quantize. So really, you're going to pick Fourier coefficients, and then one quantizes them to build the Fock space. So these modes, upon quantization, they become gravitons, which one can act with on the vacuum to create these states that we want to scatter. Here. Okay. So the simplest object that one can consider now is the scattering amplitude that involves one of these guys. So let's look at the following thing. And sorry if this is super basic. I was told to give an introduction, so apologies if it's super obvious. So what is this object? It's a scattering amplitude. So let's look at this picture. These in and out states are essentially the states that I'm preparing at scri minus and scri plus respectively. So you can think about it just by reference with that picture. Like this in state would be just these 2 particles that come in that particular case. Sorry, this is just an example. The scattering, the S matrix tells us how these things interact or how they unitarily evolve in time. So this is like a blob. This out state here is just going to be this collection, 3 particles, or it can be n particles in general. And then this guy is most interesting, which is, maybe let me just take one of these squiggly lines to represent the graviton. So this is going to be this guy. And usually, to compute this object in quantum field theory and an effective field theory of gravity is quite difficult. So the full answer to this simple scattering problem in gravity is not known, and the reason for that is that gravity is sort of nonlinear theory, so gravitons interact with themselves. So already, if you want, so at tree level, people have devised methods to recursively compute tree-level amplitudes involving these gravitational degrees of freedom, but as soon as one goes to one loop, things become very complicated already. So this is a hard problem in general, and one can make some progress in a perturbative expansion as one would in quantum field theory. So, sorry, I should say this kappa here is related to Newton's constant, so it's like 32 pi g Newton. So the usual quantum field theory approach is that we expand this thing in the interaction strength. So this is just Newton constant in this case. So we have, roughly speaking, an expansion of this form with some coefficients that are usually called scattering amplitudes, right? They depend on the states that you are scattering and on the precise interactions that you are putting in. So this would be the scattering or components of the scattering amplitude in a G-Newton expansion. So it would be the n loop amplitude, and then there's going to be some momentum conserving delta function that always has to be there. So roughly speaking, it ensures that energy is conserved in any of these processes. Okay, and people are working hard to compute these objects. Now, there is, as you know, there may be other, maybe more appropriate expansions that one can do that can give you maybe interesting information about the scattering process that are not necessarily organized as expansions in power of G Newton. So one natural thing that you can try to ask is, what does this amplitude look like in the limit when this graviton actually has a very long wavelength? So in this case, you would be performing an expansion not in G Newton, but really in the energy of this graviton. So this P is the graviton momentum. It has to be on shell, so P squared is equal to 0. So this means that I can always parameterize it as some energy omega times some null vector, which I'm going to call, sorry, just for consistency, P hat. So P hat is equal to 0. And this thing, P hat, is only going to depend on the angle at which the graviton is going up. This is the energy. So one can imagine making some progress by instead expanding the same object in powers of this energy omega. So then we'd have an expansion of the following kind. So, and now you can kind of intuitively see that when you perform this expansion, the leading order terms actually won't be sensitive to the details of the interaction. So so roughly speaking, small omega corresponds to a very large wavelength of the graviton. So this very large wavelength is not going to be sensitive or not going to be able to probe these very like UV kind of like degrees of freedom that are exchanged in the process. And so one would expect at least the leading order term in this expansion to be universal, so not to depend on the interactions, on the matter content, or on the precise type of particles or interactions in the process. And indeed, this turns out to be the case. So this was well known from Weinberg since the 60s, that the n equal to 0 term in this expansion is universal. It's all loop exact. and it's given by a very simple formula. So it has, there is actually divergence there, right? You see, I'm starting my expansion at 1. My leading term in the expansion is 1 over omega, so as omega goes to 0, this thing is going to blow up. And the coefficient here, sorry, and I should have said that the left-hand side is the amplitude involving one graviton. On the right-hand side here, we have the amplitude without the graviton with some prefactors, right? So one can, in principle, if you knew all of these guys, you could recursively kind of construct amplitudes involving more and more gravitons just using this formula. Okay, so the n equal to 0 coefficient here, so s equal to 0, is well known, computable. It's a very simple calculation, actually, just using some dimensional analysis and Stickle-Feynman rules. And it's just the sum. It involves the sum over all other external particles involved in the scattering process and their momentum. So pk nu, and then we have epsilon plus mu, epsilon plus nu. So these are functions of the graviton. Momentum p hat divided by pk dot p hat. So here pk are the momenta of all other particles, and this p hat is the part of the graviton for momentum that doesn't involve the energy. Okay, so the nice thing about this is that about 10 years ago, it was realized that this Weinberg-Soft theorem is actually very closely related to space-time symmetries. So in particular, in a very kind of different line of reasoning, one can just study not amplitudes, but perturbative solutions to Einstein's equations in a large R expansion. And this problem was studied a long time ago when people were trying to understand gravitational waves. So in particular, Bondi, Vanderburg, Metzner, and Sachs. Also in the 60s, they were setting up just the GR problem to understand the propagation of gravitational waves. And they found in the process that, when you're looking at the conformal boundary in this problem, there are certain so-called large gauge diffeomorphisms that act non-trivially on asymptotic data, and they generate an infinite dimensional symmetry algebra. So roughly speaking, what these transformations are generated by vector fields xi that are related to functions on the sphere. They're parametrized by a function on the spheres here. Sorry, I'm using different notation. F of omega d by du plus subleading components in 1 over r. So these transformations, you can use them to shift different points on these asymptotic cross-sections of the null cones at infinity by different amounts depending on the point at which you are sitting. Very obviously, these form an infinite dimensional symmetry algebra because they are parametrized by functions on the sphere for which one needs an infinite number of spherical harmonic coefficients, say, to specify. So interestingly, there was this sort of, back in the day, it was like a gauge degree of freedom that they couldn't kind of make sense of. They tried to get rid of it, but because it meant a little bit of trouble. Actually, originally, BMS observed that these symmetries, of course, exist at both scribe minus and at scribe plus, and they act independently on your asymptotic data. They're a priori not related, and then you are in trouble if you try to set up an initial, say, value problem for this case, where if you specify initial data, say on some null surface at past null infinity, and then you evolve it with Einstein's equations in time, the data at future null infinity is not going to be completely determined in terms of the past data. It's only going to be determined up to one of these BMS transformations. But what Strominger realized about 10 years ago was that there is actually a matching condition or a boundary condition that one can impose near space like infinity that relates these two BMS symmetries acting at scri minus and scri plus. And this matching condition actually gives rise to a conservation law in space-time. So, and by imposing this boundary condition or this matching condition, he was able to relate, to sort of understand the soft gravity theorem, this thing we discussed here, as a conservation law associated to the charges that generated these BMS symmetries. So, in other words, QBMS, by demanding, so there is a matching condition that allows you to define a charge that commutes with the S matrix in the sense that you get the same charge as scri plus, same charge as scri minus. He assumed that the scattering, the S matrix commutes with this object. So this is like the generator of BMS or super translations. BMS transformations. And so just starting with the identity and sandwiching this between in and out, arbitrary in and out asymptotic states, he was able to show that this conservation law corresponds precisely to the leading term in this expansion here. So this is completely equivalent to the Weinberg soft theorem. So the n equal to 0 term above.
Is there a rationale for this untitled much? I mean, can one explain it works?
Yes, actually, one can explain how it works. You can resolve space like infinity with basically like the Zitter slices, and one can show that if there is no radiation that goes through these slices, so in the ADS-CFT context, it would mean like no operator insertions on this resolution, then one can show that as you go, in fact, this is related to the later story in ADS-CFT that I'm going to describe. If you go from the past of that cylinder to the future of that cylinder, there is a natural antipodal matching that takes place. So that's one way to think about it, and yeah.
The right-hand side is purely classical, but the left-hand side is some quantum all-loop calculation of the scattering amplitude.
Yeah, sorry. So that was the next thing I was going to say. So the left-hand side is all-loop scattering amplitude, but this all-loop scattering amplitude, if I knew what it was, from like if someone handed me this amplitude, it should always admit some expansion at low energy, right? And the leading term in that expansion turns out to be all-loop exact, so it doesn't receive all corrections. And then there's going to be a bunch of other subleading terms. So maybe it's a good point to say what happens to the other guys. So the n greater or equal to 1 terms that are linear in omega, they will receive n loop. They will be n loop exact. So this means that they won't receive corrections from Feynman diagrams with more than n loops. And of course, they won't be, first of all, I should say that not even the n equal to 1 term. So the subleading term in this expansion, it is somewhat well known. So it's a 3-level, it turns out to a 3-level to also be universal. It receives a 1 loop exact correction that's infrared divergent. The finite contributions to that are not yet proven not to exist, just because 1 loop amplitudes in gravity are not fully understood. But then there is some interesting story that has to do with a whole series of expansion of terms in the expansion in omega. some of which seem to also be universal in some sense that I'm going to explain later. But I'm not claiming that we understand. So first of all, we don't even understand all of these linear terms, all of these polynomial terms in omega. Those can receive up to, at n, as I said, at n subleading order, they will receive n loop exact corrections, and we don't really understand that story. And then there are these dot dot dots here that in principle are going to be of the form omega to the m log omega to the n with m greater than n, that are going to come from yet other loop corrections that just cannot be written in such a polynomial way. So, and these are even less understood.
I see. But your point is that since you're matching the tree level on the left-hand side to a classical calculation, there's some expectation that those should match.
Yeah, exactly. So if you think about it from the strict GR question, there should be a piece in this amplitude calculation that's purely classical. And this classical piece, there's a whole story. I mean, like these classical terms, they, of course, because of nonlinear interactions in gravity, they can be all ordered in G Newton in principle. But one should, in principle, there is a map that maybe is not so well understood between essentially just solutions to Einstein's equations in a 1/r expansion and some pieces of this classical amplitude here, which are also very interesting. Okay, so now, but what the talk is going to be about infinite towers and symmetries, and interestingly, a couple of years ago, it was actually observed. So a priori, from what I just said, there is no. Sorry, I should say the n equal to 1 ones were known for a while from Cacciazzo and Strominger to be related to some enhancement, further enhancement of these asymptotic symmetries. So you can think about these BMS transformations as just enhancements, local enhancements of Poincaré translations, but there is part of the Poincaré, there is also the Lorentz group, and there is local enhancements of those. So there's 2 copies of Virasoro, and those symmetries are actually related to the n equal to 1 guys here, and one can show by a similar argument after constructing some charges and demanding that they commute with the S matrix, that they will reproduce the subleading correction. But now there is, in principle, and in fact, there was also in the Cacciazzo-Strominger paper, there is also an argument about why the n equal to 2 terms should be universal, but that lacked a symmetry interpretation until very recently. And if you care about all n terms, a priori, there should be no reason that anything nice happens. And now I'm going to just write the claim, and this was shown with some methods that I guess are CFT related, but I'm not going to have time to go through this proof. But this was shown in a paper by Guevara, Himwich, Pate, and Strominger in 2021. That these tower, some piece of this tower of corrections that are polynomial in omega, so the sub n, so a part of the sub n leading soft theorems generate a 2D symmetry algebra which is generated by higher spin current. And this correspondence, roughly speaking, was shown by basically projecting, looking at those modes. So we can project out the, one can define the following quantities. So the omega to the s, omega a, omega p hat. So these are my graviton modes. Say they only restricted to the positive helicity ones, you project out the leading pole, and then you look at the S subleading component in that, right? By taking on, like, the derivative to the S basically projects all of the leading terms out, taking omega to 0 projects all of the subleading out, and this picks out the coefficient of the nth, the omega to the n minus 1 term in that expansion. And the idea was that these things naturally, so you see now the omega dependence also drops out. These things can be mapped to operators on a two-dimensional sphere. And it turns out that they are the actual conformal primaries. It just so happens. So they are operators of spin 2 in a 2D CFT of dimension delta 1 minus S. So SL2 primaries. In a 2D CFT. And turns out that they have also some, they used some OPEs together with some resummation of of certain descendants of these guys to compute their algebra. So one can compute the algebra of these things. So those guys form a closed algebra. And it's I like to write it, this is not how they wrote it originally, but it's very nicely written in terms of some quantities. Let's call these QS. These have, I'm going to explain in a moment, they have a very natural gravity interpretation as well. They are local operator on some codimension 2 surface in spacetime, and they are labeled by some positive integer s. There is some map between these direct modes and these guys, and these guys obey the following algebra. So QS omega, QS prime, omega prime. If you compute the commutator of these two, you find the following thing. Where this is just a covariant derivative, so it's just like a dz. It's just a holomorphic part of the derivative. It's like, sorry, I should just say it's just like L1 in the 2D CFT. It's like dz in 2D. In 2D CFT, say on the plane with metric dz bar. And then there is the anti-symmetrization of this. S plus 1, Q, S plus S prime minus 1, omega. And these are just delta functions in omega minus omega prime. So this is a local. It involves this delta functions. So it's ultra local on these cones, on the cross sections of these cones. And it's well-known. This was a well-known algebra in conformal field theory. After mode expanding, this turns out to be so-called W1 plus infinity algebra.
So, Anna, could you say again what the QS omega were?
Yeah, so you can think it's a little bit of a construction, but roughly speaking, they are just they are related via light transform in like a two-dimensional light transform to these graviton modes. So they would be just the coefficient. These graviton modes are just you take the graviton and you expand it in powers of omega, and you look at the coefficients in that. And those turn out to transform like Lorentz boost primaries of dimension. It's just a fact. Because omega, you see, like this doesn't depend on omega. These are just operators defined on a codimension 2 slice, and one can check that they have dimension, that these coefficients have Lorentz boost dimension or Rindler weight dimension 1 minus s. They have a spin 2, helicity 2, because they're gravitons, and one can then play some CFT games with these things, and one can relate them to some other quantities QS that form a nice algebra. You can, of course, originally in that work, it was just directly the algebra of these guys that was computed, or other modes of these guys. But this map is actually very natural from a space-time point of view, and I'm going to explain that these QS here are precisely related to these BMS charges that one can construct canonically from a covariant phase space analysis, at least for the s equal to 0 and s equal to 1 in in gravity.
Most of these operators are below some kind of unitarity bound.
Yeah, so I'm in CFT, so here naively they don't obey unitarity bounds because they have negative dimensions. So from the 2D CFT point of view, these guys don't, but these guys do actually, because these have actually dimension delta equal to 3, all of them, and they have spin, like there is a whole tower of higher spin guys. So this light transforms maps these negative dimension guys to dimension 3 guys that have a whole tower of different integer spins.
Do you expect that G Newton will show up in this story at some point?
Oh, sorry, it does. Sorry, I set k equal to 1. It obviously, I mean, there is some power of k here. And actually, okay, there is, these guys from a space-time point of view, actually, they are very nonlinear in the field. So this bracket is only a linearization of that structure.
You did the kind of
Yeah, and also in the CFT, you only see the linear, you only see sort of the linear piece showing up.
I see, okay.
But somehow, okay, maybe we can, it's maybe like question for discussion later. Okay. So just the take-home message of this part of the talk is that gravitons, or parts of gravitons in 4-dimensional flat space in some long wavelength limit or some low frequency, although notice that I'm actually keeping all order terms in an omega expansion, so not all of them are going to be actual like soft or low energy modes, but nevertheless, there is a correspondence between these modes. Modes thereof. They correspond, they generate a W1 plus infinity algebra in a 2D CFT. Okay, and this has nothing to do with ABS CFT. Now, I thought because maybe like people are now confused, so there is some work that I thought I'd discuss, which is very much related, and it's also related to the story that I wanted to tell today. So it has to do with the fact that these symmetry algebras of these guys actually appear very naturally in higher dimensional conformal field theories when you look at light ray operators. So, where is... So I should say that the origin of these things is not well understood, but it seems like they have to do something with light cones and Lorentz algebras inside space-time, and one can play similar games also just purely in CFT. So this is based on work by Shao, by Cordova, and Shao. I think it's from 2018. So this was much before actually before this W infinity algebra was found, and it just had to do with some BMS-like symmetries that are just generated by the leading, by the S equal to 0 and S equal to 1 guys on the side. So they showed that one can find these universal algebras in unitary d-dimensional conformal field theories. So the slogan here is that there are some BMS 4, or really extended, I mean, including both supertranslations and superrotations. There are these infinite dimensional algebras in any unitary CFT-D. So I'm going to set, just for analogy with the case I've done before, just because the gravitational situation has not actually been analyzed very much in higher dimensions, I think it's very natural to naturally connect to the story. One can set D equal to 4 here. So I'm going to be focusing on 4-dimensional conformal field theories. So of course, the conformal algebra here is SO4, 2. And inside here, there is some Poincaré. like a 4D Poincaré, and inside this Poincaré there is some SL2. So I'm going to describe them in a moment what are these generators of these things. So their setup was the following. So they took a CFT on the plane, and they looked, they went to these light cone coordinates. So it's very similar actually to what I've done in space-time here, except for now we're in CFT. So these x plus and x minus are the planar analogs of these radial, of these advanced territory times I defined before. And the metric here, the CFT is like dx plus, dx minus plus d omega. So you can think about this as dz bar. And or sorry, maybe they wrote it as x perp. Let me just use their notation. And in this theory, there is a stress tensor. So they assumed that the CFT has a stress tensor, which okay, all good CFTs should have them. And they define the following operators. So there is this so-called ANEC operator. Sorry, so they focused on, I should say, they set x plus is equal to 0. So they focused on operators that are localized, they're non-local in the x minus direction, but local in the transverse directions, and localized at x plus is equal to 0. So they took integral from minus infinity to infinity, dx minus, t minus minus, x minus, so x plus is equal to 0, and then omega, sorry, x perp. So this is one thing that you can define. I'm going to describe in a moment what the connection is to the gravity story, but so far let's just be in the CFT. X minus, t minus a. So now I'm just going to drop everything. My stress tensors components are just going to depend on three things from now on, because I'm going to assume that we are on x plus is equal to 0. And then NA, okay, and these operators are very natural. If you first of all, if you integrate them, also if you look at the global mode in the transverse direction, so also integrate in x perp, this thing is just going to be the generator of translations in the minus direction. It's just what it is.
And the second line is that A subscript?
A, I'm calling, yeah, exactly. It is A because, sorry, maybe I should say perp. It's one of the perpendicular directions. So I'm calling my dx perp. You should think about it as dA, dxa.
I'm just trying to match indices. Like in the last one, you've got an A index on the left and on the right, but in the line before you.
Oh, sorry. No, sorry, you're totally right. I think I'm missing a derivative. Well, I'm tempted to say it's Ka, but yeah, exactly. This is going to be boost in the yeah, no, I think it should just be Sorry, I think it's just Ka. Sorry, I think it's not so deep. Let me just quickly double check the paper.
You want a minus. Instead of T minus A, you want a minus minus.
So this is definite. I mean, I think these two are definitely,
Right.
because this corresponds to global translations in the A
I'm
direction.
just reading the paper. It's K equals X minus T minus minus.
Oh, so it's the boost.
Oh, sorry, exactly. Sorry. No, yeah, that is really, you know, of course. Yeah, you're totally right. No, I just had a mind. Yeah, of course, because this should correspond indeed. No, I was confused because I was like, it's a boost in the T. It's basically a boost in the TX plane. So of course it cannot have an A index, right? Sorry. Yes. So this is just a boost in the TX1 plane. And this is just, sorry, P minus here, and this is a translation in the transverse direction. Okay, so these are the things they define, and crucially, while the global generators, of course, they can be, they are things that are integrated on a codimension 1 slice in space-time. So here we would find the topological operators, but more generally, one can define local operators associated to these guys by just considering modes, like integrating these guys against arbitrary functions in the transverse direction, and those are not going to be topological. But nevertheless, what they showed is that they form an interesting algebra. So let me just very briefly sketch the assumptions and how that went. So the only assumptions that they had was causality. So things that space-like separation commute, unitarity. So here they assumed that we are in a unitary 4-dimensional CFT, so I'm putting a d-dimensional CFT. They assumed that the ward identity is obeyed by the global generators. Or charges. And they also needed to assume that they looked at some algebras of these operators, and they had to assume that these algebras are closed in the sense that any operator. So of course, if I take the commutator of these two guys, in principle, we can get another light ray operator. But they assume that this light ray operator was constructed as some line integral over some local operator that you already had in the CFT to begin with. So closure. So just using these assumptions, they're able to just fix the commutators of all of these guys. So I'm not going to go through that computation. I'm just going to illustrate it for the simplest one, which is this ANEC operator, this net energy flux through scry, if you want. So if they computed the following object, actually this one is pretty easy to compute, and this comment is going to apply to all of them. So for the first observation is that causality implies that all of these commutators of these things are going to have to be delta function localized in the transverse direction. And this is because by construction, all of these things live on a codimension 2 slice of a null cone. So they have to always commute unless they are at coincident points, just by causality. So the ansatz is the and then this gives you, so Here is just causality. And by the way, this assumption should also hold in gravity. If you had similar operators of this kind, I'm going to relate in a moment to what I said before, this should also hold in that case. So x perp 1, 2, and then some coefficient. And in principle, you can have arbitrary numbers of derivatives on the right-hand side. And then what I did was to integrate both sides in x perp 1. So just to look at the global generator, the commutator of essentially translations with this guy. And so this tells us that P minus E to perp is equal to just L to perp. But this commutator, we know exactly what it is from the word identities. It's just a translation. So this is D minus of E x perp. But of course, D minus of this object is just 0. So this allows them to fix L to be equal to 0. So this is just Poincaré. So this is actually the, yeah, so maybe I should say this is 1, this is 3. And then the last step was to also fix these other terms to 0, and the way they did that was basically by using 2 and 4, and it's just essentially dimensional analysis. So just
to go below the output.
yeah, exactly. So they assumed, so closure tells you that whatever this LA is, it has to be some integral over the light ray integrated against some function, g of x minus, can be a delta function, but it can be anything else, of some phi a x minus x plus is equal to 0 x perp. And this was assumed to be an local operator in the unitary CFT. And then you can use this in this formula, and you can count the dimensions basically of the left-hand side and of the right-hand side, and you're going to find then. So in particular, they looked at the twist. So match twist of left-hand side and right-hand side. The twist is just the difference between, they define it as the difference between the scaling dimension in the CFT and the boost weight, so this eigenvalue under boosts under J01. And this implied, if you do this counting, it tells you that the twist of this guy has to be equal to -1 in for the CFT. So in general, it would be like D minus 3, and there are no such there are no such operators in their story. So in particular, in 4 dimensions, -1 obviously violates unitarity bound. Sorry, this is the twist, but you can relate it to the dimension. Okay, so not allowed from unitarity. So altogether, this implied that these ANEC operators, and this was a well-known result from before, these ANEC operators commute. And they proceeded to do this for all the other commutators. And the result was that they observed that taking a particular linear combinations of these E, K, and A that I'm going to write in a moment are going to form a nice algebra, which is precisely this algebra that people had been talking about in the gravity context before. Sorry, I'm just seeing, I'm out of time, or almost, right? Or how long can I go on for?
You can go until 11:30.
Okay, yeah, let's see. Hopefully I'll finish sooner, but yeah, so now in the same spirit, you can do a computation of all the other commutators. So and observe that the following objects, so TF, just the integral, just this local version of of this E operator, and now this R, YA, you see, it's just some linear combination of these things. They obey a nice algebra, which they identified as the BMS algebra. So the extended BMS4 algebra. And I just realized, okay, sorry, I realized that I wanted to compare it with some part of the algebra of these charges that we wrote down before. I'm just going to say in words. So TF1, TF2 is the thing we have just shown. This is 0. And then TF with R, YA is I TFG, where G was a half dA YAF minus YA DAF, and R Y1 R Y2 is R Y3, where Y3 is just a commutator of these vector fields. Okay. So now let's compare this to, so this is just a CFT, it's just a fact in CFT, but turns out that, yeah, this algebra had been found in the gravity context before, and if you remember, I wrote down this algebra generated by these QS charges, and it turns out that if you take that formula I've written down before and set S equal to 0 and S equal to 1, those two are going to generate exactly the same thing. So let me just relate it to the story in gravity. Okay, maybe I write here.
I had a question.
Yes.
You really need a CFT in that case? Could it just been any quantum field theory? Or did you use the conformals?
No, you are right. I think. Well, I think you are right. I think it can be just the QFT that's.
This part.
Although maybe this unitarity that they, this unitarity condition, I need to think about it in QFT if they would be able to. Because indeed they, well, sorry, I mean, I think in this argument where they matched the dimensions of the two sides, I think it was the delta with respect to the full SO4, 2. And then they found that there are some operators here violating the CFT unitarity bound. So if you have a usual QFT, okay, you may.
A few weeks ago, people had papers that these non-operators in CFTs that said they got a lot more symmetry than.
Yeah, I will. Yes, okay. I think. Yes. we can discuss that. So let me just now connect a little bit to gravity. So going back to what I said at the beginning, so in gravity, around actually maybe 2 or 3 years later, there was a story that, so of course there was this I should say that these light ray operators are related, or their algebra is related to the S equal to the algebra by S equal to 0 and S equal to 1 charges. So remember I wrote this QS before, which are in turn related to these graviton modes. And there is a very nice way to understand to understand how these things arise. So a few years ago in gravity, just analyzing four-dimensional, now asymptotically flat spacetimes, a priori here you don't have any CFT, you don't have any conformal symmetry or anything. But one can still, inside here there is a Lorentz subgroup. So this would be an SO 3,1, in terms of which one can reorganize the metric degrees of freedom. And it turns out that, so again, let me draw this picture. Let's say we focus on Scri plus, and we look at an expansion. So this would be like constant R surface. This would be U. You can take Einstein equations, and you can expand them at large R, and to all orders in G Newton in principle. So expand Einstein's equations in powers of 1 over R. And then it turns out that they look like this. You can show that GUU, so the GUU, so this is just, and by the way, now I'm just going to focus on vacuum Einstein equations. So GUU is equal to 0 implies an equation of this form. Sorry, maybe it's easier to just write down the equations in general. So du qs is dqs minus 1 plus s plus 1 divided by 2 cqs minus 2. And then in general, I mean, there might be some corrections here. Let me say now what these qs's are. These qs's are related to these q's I've written before. So in particular, these equations come about like this. So if you take GUU is equal to 0, that would imply the S equal to 0 equation. And this would tell you QS equal to 0 is related to the so-called Bondi mass aspect in gravity. So this tells you about energy radiated away by gravitational waves. But you can also think about this, if I were to turn on a stress tensor here in GUU, this, roughly speaking, would be related to TUU, obviously. It's like a very natural thing. And then the GUA, or GU perp, if you want, is equal to 0. This gives you the S is equal to 1 equation above, and that this Q S equal to 1 in gravity, it has the interpretation of an angular momentum aspect. This NA is not the same NA I've written down before. It's maybe just to avoid confusion. It's angular. Well, it's related, but it's not the same. But if I were to turn on a TUA here, this would naturally have something to do with TUA as well. And then there is a GAB. So, and by the way, now you can see, like on this side, if you somehow relate your light ray operators in the CFT as light ray operators associated with TUU and TUA, these would, it's very natural to expect that they would obey some algebra of this kind, and indeed this algebra is just going to be closed. It's going to be closed on just the S equal to 0 and S equal to 1, guys. But now in gravity there is also and these would be just at order 1 over r squared, and the GAB, if you also do it at order 1 over r squared, it implies that there is another charge S equal to 2. So this would be some subleading mode of the transverse traceless component of the metric. For s equal 2, the equation somehow surprisingly remains exact. So it's still completely governed in this recursive way. So the du q2 is going to be related to q1 and q0, just purely from Einstein's equations. And this qs equal to 2, first of all, it has to do, and this is what we showed in work with Laurent Friedel and Daniele Pranzetti a couple of years ago, is the conservation, the matching of these charges implies the subleading, the tree-level subleading soft gravity theorem. So it's like 1 over r to the s minus 1 component of HAB. Okay, so now, so far I'm just giving, and then you can show that if you assume that these equations hold for all higher s, which actually in gravity you cannot show. At s equal to 3, it remains exact. At s equal to 4, there's actually dots here. Because how do you get that? The higher s ones, you can show that they come from continuing to expand this GAB to increasingly subleading orders in 1 over r. And not surprisingly, you're going to start getting corrections even in pure gravity when you continue doing that. But just truncating, just looking at this part, you can show just by computing the Poisson brackets on the gravitational phase space of these objects that they obey this W infinity algebra that I've written before, which admits a subalgebra generated by s equal to 0 and s equal to 1. So now to connect to this side, a nice thing that one can check is that while in the CFT calculation a few years before, these brackets were found pretty much by brute force, so they just computed the brackets. Even if like just using CFT principles, there were some guesses involved. They had to take some linear combinations to find these nice algebra. It turns out that actually, if you just take this equation and you blindly replace this quadratic term here by just tu u, the solution to this thing, like in particular for t, it's kind of obvious that, you know, let's throw this part away, and you just get that q0 is just going to be the integral over u of tu u. So that's the natural gravity analog of this ANEC operator in CFT. But then you can use this equation for the s equal to 1 guy as well, and then you're going to get some term that's going to involve the d of q0 and tua. So it's exactly the linear combination that appears here. And this is what you can show. So there is something in that equation that actually tells you that these guys have to obey this nice algebra. And then now further, so this I haven't done, but it's a very natural thing that one can do. GAB, there is for s equal to 2, there is a prediction from this equation. There is some prediction that one can make about what TAB is that would actually enhance this algebra by another likely operator that would be sort of related to these spin 2 charges that then, you know, you would need to add a full higher spin tower of these likely operators local on these codimension 2 slices that maybe generate an infinite dimensional symmetry algebra. I'm not sure what you're referring to, but there is certainly more operators here that are related, for example, obviously to TAB, whose algebra maybe has not been computed, and it might be interesting. So, this was part of my work, but finally, more recently, there is also a connection between all of this and 3D CFTs that I was planning to say a few words about, and I can do it in 10 minutes, but also if people want to stop, yeah.
So first you had just gravity, you looked at asymptotic symmetry of just gravity, you got BMS.
Yes.
And you looked at a CFT on a fixed min-costy background and showed that these null operators also have a BMS.
Yes.
In principle, those are completely...
Absolutely. I wanted to raise some food for thought in this talk, this CFT audience, yes.
And here you're saying, well, just back in gravity, I
Yes.
can roughly identify what the null operators are.
Excellent, yes, exactly. That was the point, and there is I think it's still a mysterious connection about like why these structures, just Einstein's equations, and it's a very non-trivial computation to show that this QS, this equation implies this plot. Because here, actually, in principle, first of all, you don't need a T. You can just use these recursion relations. And when you solve them order by order in terms of these fields, right, first of all, you're going to be nonlinear in these metric degrees of freedom. There is a Poisson structure on your gravitational phase space, and you can compute the commutator of these things just using that. And doing that is actually a little bit non-trivial. It's much harder computation than would be in like CFT, where everything would be very easy. So somehow these equations provide some like bulk. It's almost like there is some like phase space realization of these symmetries, whereby you have to, you know, like somehow there are these nonlinear quantities that one has to compute, and in principle, you know, these things would have like components that are cubic in the metric degrees of freedom, and those are absolutely crucial to actually reproduce the correct algebra when you compute these things. So things like this you wouldn't see in CFT, but there is obviously a connection. But the key, I should say that naive analysis of Einstein's equations would never give you equations as nice as this. It was absolutely key to write before, you know, analyzing all of this. And this was work by Laurent Friedel and Daniele from a year before the story with the symmetries. Like they noticed that if you reorganize the metric degrees of freedom in terms of Lorentz primaries, Lorentz spacetime primaries, then the Einstein equations actually drastically simplify up to s equal to 1. Right? And then you can assume, you can say, okay, maybe something like this continues to hold, and there is this nice structure, and then you can study its implications. But the story, even in gravity, is not well understood because we don't know, for example, what s equal to 4 corrections would be.
In CFT, people don't have these IRS there. But from these like the operators you can write, and these are kind of local versions.
So there have been, I mean, there have been some paper by, I think maybe closely related is a paper by Sasha Zhiboyadov and Gregory Korchensky, where they showed that there are some W infinity algebras in CFTs, and that's probably related to this. But also, I guess they did it for 4D CFTs. So, but now I was going to say that there are these things also arise in 3D CFTs. So they seem to be quite universal. So, and maybe a little bit in a different way than they. So I should say, yeah. So this Cordova-Shao work was also for CFTD, but they had to have like a light cone, and they had to have these light ray operators. The point is that it seems somehow that, well, one can also get similar structures by looking at a time slice in usual d-dimensional CFT, so in particular in 3D CFT. So the motivation, so now this brings me to this more recent work from from last month with the Joya. So here what we have shown is that actually if you take, so this was motivated by the ADS CFT correspondence, so there is a very natural question that one can ask. Maybe, okay, so I presented the Cordova-Shao thing because, you know, it's a very nice connection to CFT, but it's not, it's sort of like, it's saying that there are these universal algebras sort of in any theory, but it's not exactly, it has nothing to do seemingly with holography, right? It has to do more with like light cones in various contexts. But another question that one can ask is whether, you know, just in the context of 4 dimensions, we know that there is a holographic correspondence that relates theories of gravity in 4 dimensions to CFTs, and one can ask, okay, so in gravity, in asymptotically flat spacetimes, we seem to have these infinite towers of symmetries, or maybe approximate tower of infinite symmetries. So how could those arise in ADS CFT? Because there we know that there is there's just SO 3,2 isometries, it's finite dimensional. But what turns out to happen is that actually you can get a similar story in this context. And the way it appears is by considering this old story of flat space limit. So if you take, so we have ADS4, we imagine it as a hyperboloid and turn it around. And anyway, so there is a bulk ADS inside, and there is a CFT living on the boundary with an SO 3,2 algebra. And if one inserts, it was observed a long time ago that if one places operators in a particular kinematic configuration whereby the operators are separated by pi. So there is a global ADS time that goes this way. There is global ADS coordinate that goes this way. The boundary is that rho is equal to pi over 2. And then the point is that in this limit, when you place your operators in this particular kinematic configuration, after suitable transforms, one can do several transforms and they all take you to similar results. Roughly speaking, one can get scattering amplitudes in flat space. So it's very natural to ask, so in a flat space limit, so this flat space limit, it depends on what the variables are that you want to consider. So there is many prescriptions, but the simplest and the dumbest one is to just take the correlators, just put them in position space, not momentum space, place them in this configuration, and you can show that in this limit, the correlation functions, for example, 2, 3, and even 4-point functions, they actually develop some delta function contact terms that precisely coincide with the momentum conserving delta function here on the flat space side. So then you can ask, how about the symmetries? And what turns out to happen is that, so on this side, if the CFT is holographic, certainly the stress tensor is going to be related to gravitons in ADS4. So one can consider the algebra of modes of the stress tensor in a 3D CFT. So motivated by this flat space limit, which by the way in my talk I had Carrollian in the title. So by Carrollian limit, I mean what people usually mean, which is that, so say I have CFT on the cylinder with coordinates t, z, and z bar. The Carrollian limit is rescaling t to c times t, so let me say c times u, and taking c to 0. So in this limit, if I have a Lorentzian CFT with metric dt minus dt squared plus dz bar, this is going to become dz ez bar plus order c squared corrections, right? So effectively taking this limit is like kind of like treating this direction to be approximately null. So now you can see that even in this library story, I mean, there they placed their CFT on a particular slice on this x, in particular x plus equal to 0, and then you had the null direction, this x minus. So here, similarly, you can guess that, if I take this c equal to 0 limit on the stress tensor or particular the stress tensor block, and then consider light ray transforms of those guys with respect to u, you're going to obtain some infinite dimensional symmetry algebras. And this was the main result, is that it works exactly like one would expect. So roughly speaking, let me just, one last thing and I'm going to be done. If we take t plus, so t mu nu, it has various components in 3 dimensions. I can take this and I can look at the sort of positive helicity modes of this. We can work in the embedding space formalism, where we promote this this operator to a spin to field in the embedding R3,2 space. So TAB in R3,2, on which the conformal group acts linearly, and then look at T plus, which I'm defining to just be ZA plus ZB plus TAB. So these are just polarizations in R3,2. So roughly speaking, I'm just looking at TZZ component in the CFT. We can consider the OP block of these operators, take the limit, take these analogs of the light ray integrals, and we can show that these sort of modes of the stress tensor after taking the Carrollian limit actually obey this W infinity algebra. So this is a well-defined object, is something that one can do in the CFT. So consider the OPE of tx1 plus and tx minus, it's tx2 plus. So this is going to be, actually, it's going to contain a contribution from the stress tensor itself. So it's going to be some integral, d3x3, and then t plus 1, t plus 2, t shadow minus 3, and then t plus x3. In general, there's going to be other contributions from other operators as well as other components, right? So here I'm just using insertion of the identity, and I'm only looking at the contribution to the plus plus OPE from a t plus. In principle, there's going to be also a t minus potentially, and also a t u or whatever, like yeah, you know, in the R3, there is actually there are 3 polarization tensors, right, that are orthogonal. Anyway, so this one can do, and then one can take this Carrollian limit. So one can take T1 to C, sorry, Ti to C times Ui, take C goes to 0 limit of this block, and then integrate over this Ui with some weight, Ui to the Si. And then, maybe surprisingly or not surprisingly, I'm not sure, but it's a little bit of a non-trivial calculation. I mean, it's simple, but this limit is a little bit subtle for various reasons that I don't have time to go into. But the point is that if one is careful and one picks out the leading contributions in this limit, after computing this integrals, one obtains a 2D OPE block of now SL2 primaries, which looks like this. So we have T plus 1 minus S1. So now the dependence is only on the transverse directions. And there is going to be, so this goes like Z12 bar divided by Z12 times some coefficient that depends on the dimensions and things of these operators. And then we have some integral over dt 1 minus t to the minus S2, t to the minus S1. And then there is some residue at delta 3 equal to 4 minus S1 minus S2 of t delta 3 plus Z2 and then Z bar 2 plus T Z bar 1, 2. So this is just the fact plus subleading corrections in Z1, 2. And if you are familiar with the way this W infinity algebra was originally found in the context of celestial holography, but okay, you don't really need like any of that. In principle, it's just a 2D CFT computation. So after performing this, you would recognize that this is exactly the OPE block of so-called conformally soft gravitons that correspond precisely to the modes of these 4D gravitons that I discussed before. So these guys, now one can show that they are just SL2 weights. So they are SL2 boost weights from a 4D point of view. From a CFT point of view, they are just dimensions, usual scaling dimensions. They will be helicity 2, and somehow this is inherited from the fact that you started with the spin 2 operators in the CFT. And if you expand this guy in powers of Z bar 1, 2, you generate the full block of SL2 right descendants in the OPE of these conformally soft gravitons, and one can show that for different positive integer values of S1 and S2, these guys, after taking light transform and so on, obey a W1 plus infinity algebra. But the way to get it from the CFT is in principle pretty straightforward, and it parallels. It's probably, I mean, most likely, although maybe not directly obviously related to what's there, because obviously here we have TAB components, right? All of this has to do with TAB components, whereas the Shao Cordova, for example, didn't involve those guys. There is certainly a connection. So I guess, apologies, I'm out of time, but I think that's all I had to say. Thank you.
Any other questions?
So, what's the punchline of this last? I mean, what should we carry away? Can you use this algebra somehow?
Yeah, that would.
Maybe a CFT.
Yeah, I think that would be, so certainly if you think about this story as related to the story of Raclariu operators in the CFT, then probably, I mean, most likely you can use it for, to put bounds on various things. So these Raclariu operators originally, they were used in CFT in this conformal it's so-called conformal collider bounds. So one can bound, say, relate the anomaly coefficients that would appear, for example, in the stress tensor 3-point function in higher dimensional CFTs. So there is always the stress tensor 3-point function in any d-dimensional CFT is parameterized by 3 numbers, and one can relate 2 of those numbers. One can put constraints on those using these Raclariu algebras. And now it's an interesting question which has not been asked yet, because this, I mean, okay, this is, I don't really understand. This Carrollian limit is subtle, and it might be a lot of things that are confusing there, but it's a very interesting question to try to understand what one can use it for, and in particular whether one can use it to say something about scattering amplitudes in 4 dimensions, because this is what hopefully this will be good for, if anything. Yes?
How important is unitarity?
In this part?
It's like way back when you could do
Yeah.
or something like that.
Yeah, this here it was not, so on this side it's actually not important at all. It just follows from, it's very different. The calculation that we did recently is very different in spirit to the one that has been done there. So there it was more like bootstrap kind of computation where they used just symmetry principles and causality and unitarity to fix the form of those OPEs. Here, the only thing that one has to do is to take the OPE block of the stress tensor. You know that that's determined by the 3, you look at the contribution from the stress tensor to it, you know that this is determined by the 3-point function. The 3-point function is fixed in terms of just 2 complicated structures, but there's only 2 independent coefficients that appear. And then you take the Carrollian limit of that. I mean, there's just a formula for this. And the remarkable thing is that when you take this equal to 0 limit, I didn't have time to write it down, but this whole structures, like these complicated structures, collapse to just one single weight shifting operator that's super simple, acting on the scalar 3-point function. And then you can take the limit and perform these integrals at the level of the scalar 3-point function. So you have to renormalize your operators in a way dictated by this flat space limit, because roughly speaking, you want both boundary propagators in ADS to be normalized in the same way as, say, the plane waves or conformal primary wave functions that you would use in flat space to establish these algebras, right? These were inherited from scattering amplitudes. And then after taking care of all of that and acting with simple weight shifting operator on the scalar guy, you land on this block. So there was, as far as I can tell, there's, and I mean, okay, of course, the stress tensor you started off with, they live in a unitary CFT. We assume that they have dimension delta is equal to 3. And
Could you do similar things with, I don't know, conserved currents?
we have done for conserve, and you get exactly for the gluon. For example, you can say photon, obviously, like a billion currents, they have vanishing 3-point functions. That's totally consistent with the fact there is no photon 3-point vertex in flat space. For gluons, there is a similar formula, you do exactly the same thing, and you get the S algebra. There is another infinite dimensional algebra, that's the S algebra with the correct. It's basically guaranteed by the fact that, roughly speaking, when you take C goes to 0, this SO3,2 becomes Poincaré, and Poincaré representations, you can always decompose them into SL2C1s. And this map basically implements that decomposition, because these are just sort of the wave functions for those SL2C representations. So at some level, it's not surprising at all that this can be done. But yeah, and we've done it also for scalars. So like the simplest thing that you can do is to just take a current or a stress tensor with scalar And then there you can show that you get the whole tower, these towers of soft symmetries. They just come from a simple 3-point function in the CFT, in this expansion. I mean, that's all there is. So in that sense, I mean, for example, for current scalar, the 3-point function, there is just one unique structure. So it's literally the tower of soft gluon theorems in that case is completely determined. Sorry, actually also for the stress tensor, so it's a unique structure when you have scalar, and spin L, right? So that determines completely this towers of soft theorems, and in some sense, I guess, explains why they are universal. So I mean, it's just, it's whatever that thing is, unique thing, and then you just expand it out. But then, of course, you can have other contributions, like in a stress tensor scalar, you can also get the stress tensor. So then those, in fact, be very interesting to look at the corrections, and those should teach you something about scattering amplitudes, I think, and about these corrections to the soft theorems. So this, of course, is not the full story, because, as I just said at the beginning, somehow these things only reproduce some pieces in the story, in the soft theorem story.
Sorry, your talk was about asymptotically flat, right?
Yeah.
So you don't specify what is inside.
Yes.
So if you do specify, take for instance Schwarzschild black hole, are you able to get more precise data?
Well, I haven't done this yet, but I think it is a good thing that I want to try to do in the future. Like, for example, you can take even empty ADS and try to understand how, I mean, first of all, okay, I don't want to say anything that I'm not sure about, but it's not crazy to think that in just empty ADS, if you like do it in a particular convenient gauge, if you reorganize, if you look at Einstein's equations in an appropriate expansion, where you identify the analogs of this Q, then similar nice things are going to happen. I think that's...
So people do not know how the horizon emerges in this approach.
No, but I think I don't see why we shouldn't be able to know in the next couple of years. I mean, based on this. So I think, yeah, it's something I'm planning to do next, but I'm slow, so yeah. Maybe others are going to do it meanwhile.
People also thought about like taking the exponential of this operator, like the light rays, because if you do just scattering of like QED, QCD of soft scattering,
yeah.
the object you would put is actually the Wilson line, not the gauge field.
Yeah. No, that is there is a whole story in flat space about those Wilson lines, but so far, I mean, a little bit at the subleading orders as well. You can do these, and these are related to these Fadeev-Coolidge dressings in CFT. In just flat space. I mean, whenever you have massless particles, there is these long-range interactions, and you need these Wilson lines.
But in gravity, there should also be corrections, because when you insert multiple T's, they can exchange a graviton, then you get
Yeah, exactly. And I think even there, I mean, people have focused on very simple things, but I think there may be some, well, in part because they don't really know like how these things interact in the subleading orders, but I think it's something that certainly one can try to understand. And yeah, honestly, I mean, I want, you asked this question, like, what is this good for? And I think, yeah, maybe we don't know exactly what it's good for yet, but hopefully it will be good for something, and we should try to think about what that thing is.
Any final questions? If not, let's thank Anna again.